Hello, welcome to session number 16 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and in this session I'm going to present yet another very important component which is used in microwave and millimeter wave circuits, which is called BALUN. And the function of the BALUN is to convert a differential input into a single-ended or a single-ended input into a differential. So what do you mean by differential signal? So the signal which is 180-degree out of phase, for example, a sine wave. So a 180-degree out of phase of that sine wave would be a differential signal, right? So two signals which are let's say two sinusoidal signals which are 180-degree out of phase would be called differential signals, right? And a single-ended signal is with respect to the ground. Okay, so in case of a differential lines, the ground basically is the center compared to the two voltages, right? So that's what a differential signal is. So now how do you generate it, right? So there are few ways of doing this, right? So I'll tell you, BALUN can take various forms. There are four kinds of BALUN. So first kind of BALUN can be a lumped BALUN. Okay, a lumped BALUN uses lump components to make a high pass low pass network. Okay, so it is a high pass low pass network, right? So that's a lumped BALUN. Next is you can use a transformer, right? So basically a transformer can also be used to convert uh, a single ended to differential. So what happens in a transformer, for example? Okay, transformer would have a primary, and hang on a second. So transformer would have a primary coil and let's say two secondary coils, right? So let's make two small versions of this coil. Okay, so something of this nature. So bear with me a little. Let me. Okay, so it is going to have primary as the input, right? And so basically you will give input to one side, and then there is a center tapped secondary, like over here. So that's a center tap secondary, and then you can have differential output, right? VOP, VOM I can write here. Okay, now this can be laid out. Okay, so there are two outputs, VOP and VOM, which are going to be the differential outputs, and then you are going to have VI as the input. Now this is a form of a coil. If you want to make, you can, this is based on magnetic coupling, right? So that's how a transformer works, right? So this is usually, if you want to make a BALUN which is transformer based on a chip, you will make basically three coils, and these three coils will interleave in such a way that there is a sufficient coupling between them, right? And then you figure out a center tap, and that center tap would basically result in two differential signal outputs, right? And the phase balance and the amplitude balance really depends on the tap, right? So it is very critical in the design of a transformer to figure out what should be the center tap. So that is the difficulty level. Okay, the third one is you can have a divider followed by a high pass network and low pass network. So this is going to be what you call a, a mixed strategy. You have a distributed divider and a lumped high pass low pass network, right? So you can be having divider plus low pass high pass network, right? So this is going to be a lumped plus distributed kind of a balun. And the last one is the the very famous one is Marchand BALUN. And this Marchand BALUN is going to be pure totally distributed components. So it is going to use two coupled lines which are lambda by 4. So if I was to make a Marchand BALUN, so let me just put these aside so that you have an idea of which one is what. So in this case, this is going to be your transformer thing. Okay, so this is your transformer. Don't worry about the numbering scheme. Okay, so this is one BALUN. Other one is the high pass low pass network. So you can make a high pass low pass network BALUN like this. Control C, Control V. Okay, now you can reduce the number of components in this distributed or sorry, the lump component BALUN, because there are some components which are really there for the balance, the phase balance and amplitude balance. So that control you will lose if you do this. Format, rotate. This is okay. So I'm going to do a high pass low pass network, right? And then there are two capacitors. So let me further reduce the size to half the value. This is so horrible. Bear with me. Okay, I'll just get done like this. Okay. So I'm making a high pass low pass network. So what you are seeing is a high pass network, right? Okay, so this version is a high pass low pass BALUN. Okay, so this is going to be this one. Okay, so the way this works is okay, the way this one works is this capacitor inductor capacitor. Okay, this capacitor inductor capacitor acts as a low pass network. So if I have an input port over here, P1, so I can take this one. Okay, so I give an input over here, and one path would be a phase lead, which will be a high pass network here, and then there is a lag, which is a low pass network here. right? And so this will give you a 90 degrees of lag, 90 degrees of lead over here, and the total effect would be a 180-degree phase difference between VOP and VOM. So this is how a lumped balun high pass low pass will work. Then the next one is going to be a divider plus high pass low pass. So what you can do is you can take two of these, right? And you have already seen an example where I designed what is called a divider, right? So you take two of these, and then after that you are going to put here a network which is going to be a high pass low pass. So I can basically just, so you can do this. So that will be your high pass network, correct? And then you can have a low pass network, right? So this will be a mixed kind of approach where you have a part of a circuit which is distributed and then a part of a circuit which is lumped. Okay, and you can make it really broadband. Okay, so the divider has to be broadband, and then this circuit which is high pass low pass, it can be designed to be a broadband. Okay, so this one would be this divider plus high pass low pass network. And uh, let me also put here a resistance because this is a Wilkinson divider, right? So this is a high pass low pass network. So this is a Wilkinson divider, So let me put here. So in between you would have a resistance. So let me very quickly do this shape. So roughly I'm not good at drawing. Okay. So something like this is there in between. Okay. So this would be another approach of a lumped plus a distributed. Uh, then there is this Marchand BALUN, which is very commonly used in chip design as well as in something on a PCB or a laminate. Like we are going to use a LTCC version of it, right? So in this case, what you have is a lambda by 4 line and another lambda by 4 line following that, and then there is a coupler, right? So if you remember, we did a coupler, right? A coupler has a certain spacing and a width, so you have to design this for a certain spacing and a width, right? And this side is open circuited, so this side is open circuited and this side is your input. So what you do is you put your Vi on this port. So you put Vi on this port, and this is open circuited, and this is just connected. So this is just connected over here like this. Okay, and your output is over here. These two sides are basically shorted to ground. So this side and this side. Okay, so and the output is over here. Now the issue is the impedance ZO is 50 ohm, for example. That would be equal to, so ZO, Control C, so Control V. So basically ZO is equal to ZOE square root of, right? So what you have into ZO. So this is will be your characteristic impedance, right? So we have to design the same as we design a coupler. We have ZOE and ZOO. We have designed for that. We have designed a certain width and a certain spacing. So in this design also, we will have that same design formulas for a given width. Okay. So for this given width, we will have the same formulas which are based on this even odd mode impedances. So this will be the width, right? Just 1 second. Right, and then there is this spacing based on the even odd mode coupling. And the idea is, if you want this balun to have a symmetric response, the even mode impedance is higher than the odd mode impedance, right? And this even mode impedance has to be high, right? So that way you can uh, so what is the even mode impedance? It is just there are two capacitors, right? Two capacitors to ground, right? And then the odd mode impedance is that capacitor to ground plus the coupled capacitor, twice of that, right? So that's the odd mode impedance. So now if you increase the coupling, right, you are going to affect the odd mode impedance. But if you increase the capacitance to ground, you will affect the even mode impedance. So if you remove the ground itself, right, or if you move it away, then you are increasing ZOE, and then you are reducing ZOO, right? So there are equations, or there is a certain coupling, right? So you design this for a certain coupling. Okay, next is that the impedance over here, okay, which will be Zin will not be Z0, right? So let's say impedance over here is Zin. Okay, so the impedance seen over here would be Zin, and this will not be same as ZO, right? So you need another piece of line. Okay, you need another piece of line over here. Okay, so you need another piece of line over here, like this. To transform Z into Z0. So then you will have ZA, right? And this ZA would be equal to, so you need a ZA is equal to square root of Zin into Z0. So ultimately you are trying to match to Z0, right? Okay, so the overall design would be, you design it for a certain ZA, a quarter wave line, which will result in ZO, and your outputs would be over here. Okay, so this would be called a Marchand BALUN, which is totally distributed. So we have got four baluns here, right? First of all, at where to use which one. So for low frequencies, when the transmission lines are going to be very big, so I'm going to use either a transformer or a totally lumped balun based on high pass low pass network. The issue would be laying out this balun, right? But anyways, its layout is going to be smaller than the distributed balun, right? And when you go up in frequency, let's say Ka band, K band, Ka band, or Ku band, or even X band, this Marchand balun is going to be very, very good to do. Okay, now where are they used? So whenever there is a differential to single-ended or single-ended to differential conversion, you will require these balun, right? So what we are going to do is we are going to design this one, which is a fully lumped, and this one, which is fully distributed, right? Then it's an exercise to you to implement these two, right? Okay, so you'll find lots of papers doing this. So let's jump into ADS. Okay, so in ADS, I've created a folder, and I'm going to create a new schematic, and I will call this as uh, let's say BALUN lumped. Okay, let me make sure I'm recording. Yeah, so I'll call this balanced lumped. Create schematic. Now all I need is these resistors. So I'll just use lumped components here. Okay, so I need an inductor which his value is, let's say, LS1, and I would say that it is ideal, so this portion is resistance is not there. Okay, then I need to just create that structure which I have shown you here. That structure I have to create. Rotate. Okay, 1 and 2. Then I need capacitors for high pass section. So I would say CS1. Okay, so I'm going to have two capacitors over here like this, correct? And then I am going to have capacitors here also, correct? So that's that. Now, the for the low pass section, there are two shunt capacitors, right? One on the input side, the other on the output side. Now, if I was to do the analysis, I can assume that these two come in parallel. So the net capacitance over here is twice of CS. So that's that. Okay. And then there are ports where, okay, there is one inductor which I forgot. Okay. Now, this is your lump balun. Only problem is now for you is to design LS and CS, for which I'm going to write equations, right? So LS would be equal to uh, Z0. So first of all, I'll write I'm designing for a certain Z0. So that Z0 is 50, correct? And then I am going to design for a certain frequency F0. Let's say F0 is 10 gigahertz, right? And then I will have LS1. The LS1 will be Z0 divided by SQRT of 2 into pi into F naught. Okay, so that is your LS. And then CS1 would be equal to 1 over twice of square root of 2 into Z0. Okay, and okay, so now we have the equations written. Now there are three ports here, right? And then the fourth port is terminated into 50. This basically is just that it provides you a control over amplitude and phase imbalance. So you can adjust this to adjust amplitude and phase imbalance. But for now, as it is ideal, I am going to just keep here a 50 ohm termination. Okay, and then I'm going to put the ports, uh, simulation as parameter. So I have terminal in as the input. Then this is second port, this is the third one. Okay. Okay, so I'm done with this. I'm ready for simulation. So I'm going to do simulation as parameters. And I'm going to simulate from, let's say, from 9 to 11. And by the way, this lump balun would have, because these Q of these components is very large, right, or very high, then the bandwidth of the balun is going to be very narrow. Okay, so you have to be prepared for that. Okay, now first of all, I'm going to look at the return losses S11, S22, S33. Okay, so there's something wrong which I forgot to do. This is twice of CS, sorry. This is twice of CS. Correct? Yeah, now it will be okay. Okay, so now we have return losses close to 50, right? You can also see this in rectangular chart. S11 dB, S22 dB, and S33 dB. Okay, so return loss is better than, let's say, 20. So this is your lumped balun. Okay, so now that you have this, now we have to establish what happened to the phase. Okay, so S21 and S31 will be 3 dB because the power is dividing into half. S21 and S31. Okay, now notice that this is really narrow band because, beyond this you have the amplitude imbalance here, right? So on the two sides of the frequency you see the amplitude imbalance. Right. Now let us look at the phase. The phase imbalance should be less because one is a high pass network and other is a low pass network. So what I'll do is I'll go to S21 add phase and minus from it S31 phase. This should be 180 degree. Okay, so this is 180 degree and then you have got phase imbalance. On one side it is 0.7 degrees, other side it is 0.8 degrees, right? And at 10 it is exactly 180. So now this is a lump balun, but this is very narrow band, right? Because you are not able to maintain amplitude and phase balance, right? But then when you put the components with certain Q, then this condition will be not that bad, right? So that's what will happen in practical design, but then it will be difficult to achieve the amplitude and phase balance, right? So this is a lumped balun. Now let's shift our focus to a distributed balun, right, which is a Marchand balun. So I'm going to teach you to design a Marchand balun. Now all you do is you go to the coupler and you copy this file, or rather you just say file save as, and you call this as balun design, BALUN design. Okay, so once you have saved this as a balun design, coupling coefficient is 10 here, right? So I'm going to make it somewhere around 7, right, or 6 or 5. See what happens is, okay, this is what I want to explain also over here in a Marchand balun. What happens? So let me insert a new slide. Okay, so if I was to plot across bandwidth, uh, S21 and S31, right? So what will happen with the coupling coefficient? Just bear with me. Okay, so I have a frequency of interest, let's say, over here, right? And then I have the response. So I'm going to draw 3 responses. So this is a response, okay? And I'm looking at, so rather put it at here as 3 dB. So I'm going to put a line which is 3 dB, for example. Insert shape. Okay, so let's say this is 3 dB line. Okay, and this side is a frequency, right? So anyways, okay, so this axis is frequency, and I am looking at center frequency FC, right? So basically this is your center frequency FC, correct? And then on this axis I have got attenuation in dB, and I will mark this as, come on, okay, and I'm plotting for different coupling coefficients, right? So this is a certain coupling coefficient, and let me draw another one which is doing something like this. Okay, so as you increase the coupling coefficient, okay, the bandwidth is going to keep increasing, right? And the nature of the curve will keep on doing this. So I hope you understand what I'm saying here. Okay, so edit points. Okay, so the bandwidth is keeps increasing, and the loss, okay, is 3 dB, right? And there would come a point where the response would be, so you are keep increasing the bandwidth. So next I would expect this to happen. Okay, so don't worry about this. I will adjust this. Okay, so what will happen is this. Okay, your bandwidth has increased, but you see that you will have a compromise on the return loss. Okay, so basically you can design for a certain bandwidth, but then you have to sacrifice the return loss, right? Or what you call the insertion loss, which basically shows up in return loss only. So you can design a broadband balun using Marchand, but then if you keep on increasing the coupling coefficients, the bandwidth is going to keep on increasing, but then you have to sacrifice the return loss. So I would assume that around 7.6 is okay, or 7.5 is okay. Okay, so now I'm designing for that, and Another thing is that the height of the substrate. So if you remember, I was talking about the even and odd mode, right? So I want to keep the height to be large. So I'll put 379, right? And then it will be h micrometer here. H micrometer into meter. Okay. So then the width of the line is 367 and the spacing is around 40 and the length is around uh, so this portion I want to take off, so this I don't want. Okay, so the length is around 3594, right? So we are going to design with these specifications, right? So let's go to momentum. So I am going to make a new layout and call it Marchand. Okay, Marchand BALUN. Okay, so what I need, okay, is a line which is lambda by 4, right? And that basically is this one, 3594. So the twice of this, right? So the twice of this, so lambda by 2 is going to be twice of len underscore micrometer. Okay, plus I'm going to add a gap of 200 micron. Okay, plus I am going to uh, uh, have 200 or 300 micron on left and right, so basically 600 micron left and right. Okay, so that is going to be the length of a line. So equations, okay, around 8000 micron or 8 mm is the length of the line which I am going to draw. Okay, and the width is going to be 365 or 67, doesn't matter, and then I will draw a coupled line. So let's go ahead and do that. Momentum, so I am going to draw it on M7, and by the way, this is 97, 97, 97, and then 97. So there are 4 of these which I'm going to use, and then M3 would be the ground, M7 would be the structure where I draw the structure, and then I have a VR6, VR5, 4, and 3 connecting them. Okay, so let's do that. Okay, insert coordinate entry. Rather, let me just do one more thing. I don't want discontinuities nearby, so let's do 800. So that is 8200, roughly 8200. So that's what I'm going to do, 8200. So I'll say insert coordinate entry absolute 0 0. Okay, and then I'm going to say insert coordinate entry, and then it is 8188, right? 8188 roughly, and then it is 560, 565 or something like that, 565. This is rough numbers will also do, say okay. So that's the length of your line, right? And then I need another line which is going to be insert coordinate entry. Okay, let's say how do I do it, 5000 sorry 3590, 3594. So 3594, so I will go 3594. Okay, so 3594, right? And then I am going to have a width as 565, right? Relative, say okay. So that's that. So that's the piece of the line which I'm going to connect to the center of this. So that's the center. Another one is connected to the center. Okay, and then I'm going to move this 100 apart that way. So edit, move relative. I'm going to move that 100. Okay, and this one also minus 100. Okay, now I want to put two vias here and there, but before that I want to create a gap. So let's say the gap is 40. So I'm going to say minus 40, correct? And so we are set with this, and I just want to create a via here. So okay, 565. Okay, and then I'm repeating that on the other side, right? Okay, so now this is done. Okay, all I need is I need to know the impedances over here so that I can connect, and then I need VRs over here. So what I'm going to do is I'm going to choose this is 565, right? So 365, insert coordinate entry, 365, 365. Okay, so this should be via 6, via 6. Okay, so this has to be kept somewhere in the center. Okay, and say edit, move relative. I'll do 100 and 100. Okay, so this one is position, and same thing I'll do on the other side. Edit, move relative, say minus 100 and plus 100. So that's centered. Fine. So next I am going to select these two and copy this to via 5. So copy to layer, via 5, via 4, via 3, and then metal 6, metal 5, and metal 4 is going to be there anyways. So we are done with the via placement. Next is the ground plane. So ground plane is M3. So I'm going to go from the center, and roughly 3700 is the lambda by 4. Yeah, 500 is okay. So this is over here somewhere like this, and I'm going to copy this and extend it out. Okay, so this is my structure. There's going to be port 1, 2, and 3. Now, this is an intermediate run, okay, because I have to match it, right? So I would need few iterations, but the equations should be very close, right? Uh, okay, so let's put here a small gap. Edit merge union minus intersection, and this one edit merge union minus intersection. Okay, this is done. So this is my BALUN design. So I'm going to put here 1, then 2, and then 3, and then 4, and then 5 and 6, and then I have to choose the ground to be, so P1 and then P4. P4 is on metal 3, correct? And P5 is on metal 3, and P6 is on metal 3. Okay, so we are done with this. Okay, so what? This is P3. P3 is on metal 7. Yes, and then P6 is on metal 3. Yeah, so now it's okay. Okay, so now we are done. We will create a EM setup. In that, I'll go to ports, and in the ports, I will do the 4 as a reference to 1, 5 as a reference to 2, and 6 as a reference to 3. So we are done with this. Then I'm going to look at the EM preview of this. So before that, let me also set the frequencies. I'm going to go from 6 gigahertz to, let's say, 14 gigahertz. And 50 is okay. And I'm going to save the currents for all frequencies. And mesh, I'm going to enable edge mesh, transmission line mesh, and modeling. So I'm going to look at the preview. Okay, so my Marchand BALUN basically looks like this, right? So these are lambda by 4 lines which are shorted on the ends, right? And if you are worried about the connectivity, then there is a nice tool here which provides you information on solid connectivity. So if you connect anything, it will just color only those metals which are connected. So in this case, this metal is not connected, right? This is a lambda by 2 line which is not connected, and remaining are connected to ground, right? So that's a correct layout. Okay, so now once we are done with this, I am going ahead and do the simulation. Okay, I'm going to put you on a pause. Okay, so we are done with the simulation, right? Now what I have here is S11, S22, S33. Now these are not matched to 50, right? Now what I'm going to try to do is, okay, M3 and M4. These are on the 2 output ports. Okay, so this is 112, and this one 100 and M3 is 100 ohms, and this one is 134 and 112. Let's say 120. Okay, so the phase is okay, right? The phase is 180, and then of course it picks up. Now what I'm going to do is I am going to, this is half the design. What I want to do is a proper termination, and then these things will make sense, right? So what I'm going to do is I am going to say 100 and how much was it? 100 and, where is it? 130. So I'm going to do 130, or rather 120, let's say, between 112 and 130, 120. 120 ohms into 50 ohm, square root of that. So I need a 77 ohm line, right? Or if it is a 130 into 50 and square root of that, 80 ohm line. Okay, so 80 or 90 ohm line I need. Okay, so I'm going to go to line gal. Let me go to line gal. Line gal. Line gal. Tools, line gal. Okay, so I'm going to synthesize a quarter wave line, which is somewhere that. Okay, so epsilon r is 5.92, and height of the substrate is 300 79 micron. Thickness is 9 micrometer. This is 5.86 and 10 delta is 002, and I'm interested in 80 or 90 ohm line, which is 90 degrees. Want the result in micrometers. Synthesize. So this is 146 and 80 ohm line would be 203. Okay, and 70 ohm line is, because what comes out here, calculator, 100 and 112, 120 into 50, square root of that, 77 ohm line. Okay, 77 ohm line. Huh? Doesn't make sense. Just one second. This is 100 ohm line. This is 90 ohm line. 146. Okay, so let's take 146 roughly. Okay, and put another section of line which is lambda by 4. Clear mesh. Okay, so here I am going to say is 3820. So I am going to take a line whose width is 120 or 130, right? 130 roughly. And I am going to draw from here. So not on this layer. I'm going to draw on M7 and this one. Right, so I am going 100 this way or 400 this way or 500. 400 is okay, 500. And then I'm going up to here, and then I'm going 3800 something. What is the line cal? 3820. 3820. 800. 820. Roughly here. Okay, so I'm going to take this section and repeat it here and then flip it out like this, and now my ports are over here, correct? So I'm going to drag my ports out of here, drag them out of here and place them over here. Okay, so we have this structure, and this I'm going to remove. M3. So this I don't want. Edit, merge union, and then this I don't want, so edit, merge union. Okay, so I am going to adjust this dimension, so just one second. Okay, so we are done with this. I'm going to hit simulate once more, right, and see what happens. So EM and hit simulate. I'm going to put you on pause. Okay, now you'll see the transformation. Okay, so it is still simulating. Okay, now you see that we are in the right range. Okay, and this match should improve, which you are seeing in S11 over here, the dotted ones, right? Similarly over here you can see this in S22 and S33, they're improving, and this should come to the center, and this should come like 3 dB, 3.8 or 4 dB on both. This should come to be 180 phase. Okay. So let me adjust these graphs. This is your return losses. This is your S21 and 31, and this is your phase difference. Okay, let's see what has happened here. Okay, so the length of the line is not sufficient enough, right? But then you will see that we are in the right ballpark here, right? And what I want to do is I want to minimize the gap between the two, right? Because this is S21 and 31, right? And I want this matching to center here. So that means that these lines have to be longer, isn't it? Another thing is, yeah, so EM clear mesh. Okay, so I am going to make them, so I'm going to do 2-3 iterations, not much. Okay, I'm going to add 200 micron more. Move relative minus 200. Okay, this is one thing which I have done. Okay, and B, let's look at the return loss. Can I trade this with that? No need to. The thing is, this is asymmetric, right? And this is 179 and 180. So this is your phase balance. This is around 180, right? So this is across. So we are interested in 9 to 11. Okay, so we want this to be 180. Now, okay, so once we have done this, let's put these back. Okay, one more thing which will happen is that this line has a loss, right? And this is lambda by 4. So I want to make sure that going from here to here, this is 6,800. So 3,567. So it should be around 7,000, isn't it? So I have to make these bigger, isn't it? I have to make them bigger. Okay, so to make them bigger, so this is 3,800, 100 micron bigger. Okay, so I have to make it 100 micron bigger. So roughly 101. Okay, fine. I'm going to use this for measurement. So I want to move this guy to here. So this is 100 micron bigger, isn't it? And same thing I'm going to do on the other side, right? So okay, so this is 100 micron bigger. Okay, and I have to pull these 100 micron to the left. Edit, move, relative, minus 100. Okay, and this will be plus 100. Okay, so now measure going from here to here is around 7,000. That's fine. And then I want to show you something that notice 3.1 is lower. This imbalance is because you are catching lambda by 4 from here and another lambda by 4 from here. The source is over here. So what about the loss of this line? So basically this line has to couple more to match up, right? So what I'm going to do is I'm going to move this up by, let's say, 15 micron. Okay, wrong way. To move this up by 15 micron, it should be 0. Okay, done. So now let's simulate this again. Okay, and I'm going to put you on pause because I'm going to do 1 or 2 iterations. Simulate. And I'm going to put you on pause. Once it's done, I'll come back. Okay, so we are done with the BALUN simulation. We have a certain amplitude imbalance, and let's look at the worst case amplitude imbalance. Let's say at 10 we have 3.9, and the other branch we have 3.7, 3.4 and 3.7. So we have 0.3 dB worst case amplitude imbalance, and then we have a phase imbalance in your band. The phase balance is within a degree, right? So that's basically a BALUN, right? This is your return loss, and what I'm going to do is I'm going to stop here because this is just a first cut design. You can do a lot many things with the BALUN to improve its performance with the Marchand BALUN, right? Like for example, you can work with the ground plane, increase the even more impedance by cutting out slots in the ground plane and stuff like that. Just before we go, let's look at a little bit of visualization, which is my fun part. Right, so let's look at currents, and uh, I'm interested in 10 gigahertz, and I want to put the power in port 1, and I'm going to change this to, okay, so this is what is happening with the Marchand BALUN. So power is being divided into half on the 2 branches, and they are 180 degree out of phase, equal in magnitude. So that's what is happening. Now a lot can be done to improve the performance of this BALUN, and I will leave it to the audience, because they can read a number of papers on this Marchand BALUN. There are lots of modifications to this Marchand BALUN, and they can improve the performance of the Marchand BALUN. Okay, thanks a lot. Thanks very much.